Today we have an incredible story to share with you. Building a bionic arm controlled by sEMG signal and embedded machine learning. Over the past year, we have poured our hearts and soul into this project, overcoming challenges, making breakthroughs, and pushing the boundaries of what possible. We can't wait to take you through the every step of this remarkable adventure. So let's get started. Imagine a world where individuals with limb disabilities can regain their mobility and independence through the cutting edge technologies. Our project aims to make this reality by developing a bionic arm controlled by sEMG signal and embedded machine learning collected from the forums. It was an ambitious endeavor, but the potential impact is immeasurable. In the early stages of our project, we focus on working with a single sEMG sensor to detect basic hand movements, such as closed fist and an open fist. We meticulously analyzed the data we collected from the sensor and crafted an Arduino Uno code to control the movements of our bionic arm based on these detected signals. The initial result was promising, and we felt a surge of pride in our accomplishment. However, we soon encountered a significant hurdle: noise in the sEMG signal. It felt like we were banging our head against the wall, struggling to find a solution. We embarked on an intensive period of research, diving deep into the signal processing techniques, exploring various algorithms. After countless hours of brainstorming and experimentation, we developed a sophisticated filter code to denoise the sEMG signal. This breakthrough allowed us to minimize noise impact and significantly improve our hand movement detection accuracy. With the noise issue under control, we are ready to expand the capabilities of our bionic arms, incorporating more complex hand and finger movements. For getting the complex movements, the signal from the single sEMG sensor become so discrete that it's hard to detect a single feature. We need to do something. So we discussed it with our professor, Dr. Khaza Iftikharuddin Ahmed. He suggested using a deep neural network and more sensor to perform this task. We discovered the Edge Impulse platform. It provided us the tool and resources to train our machine learning model. Initially, we collected raw SEMG signal using Arduino Uno and recorded them in CSV format using Microsoft Excel. We then transferred this CSV file to the Edge Impulse platform to train our model. The result was impressive, with a high accuracy in detecting the hand movement. However, we faced hurdles. We lacked the capability for live testing. Our faithful companion, the Arduino Uno, had served us very well during the prototyping phase. However, as we ventured through the realm of running complex machine learning model, we realized its limitation. We understood that we need a more powerful board to elevate our project to the next level. We need more capable board like STM32 or Arduino BLE33. To overcome this obstacle, we decided to acquire the Arduino 33BLE. After ordering it from the Amazon and obtaining all the necessary firmwares, we successfully connected the Arduino BLE33 to Edge Impulse platform. Finally, we had the capability to collect the live sEMG signal from our forum and test our machine learning model in real time. We were expecting that we were started collecting live data using the data forwarder, performing classification, and testing our model prediction. It was exhilarating moment seeing our effort come to life. We downloaded the model as an Arduino library through the deployment section of Edge Impulse. But the journey didn't end there. We need to deploy our machine learning model into the Arduino BLE33 and integrate it with our custom sensor and data collection code. Now it's time to integrate our custom sEMG sensor with a machine learning modeled code. With the help of sEMpulse resources, we navigated through the library, reviewed examples, and began to understand how to collect data and store them in the buffer from the sensor. Integrating our custom sensor with a machine learning model proved to be very complex. We wrote a code to collect sEMG data, processed it into the root mean square format, and stored it into the static buffer of the machine learning model. It took hours of coding, debugging, and fine tuning, but eventually, we successfully integrated our data collection code with the machine learning model. We eagerly tested our live sEMG data, expecting accurate and precise prediction from our model